Okay, welcome to Unit 5 Matrices, and since I'm not in school today, I'm going to do this as a video lesson. So here we see we are in Unit 5 and matrices. So maybe the first place to start here is just to kind of take a review of our trilogy. I talk about the algebra trilogy of our semester 1, and let's think about what we've done here. We've done vectors, you remember that, and then complex numbers we just finished up. Hopefully we spent a lot of time on that. And then our last book in the trilogy here is the Mockingjay component, which is matrices, and M goes with M, and so that's where we're heading to next. I can't start a unit in semester 1 without talking about our nice sandbox here, and so but the reason I do this is the analogy is really important, that what we're doing now is really moving to a new algebra sandbox. And if you recall what algebras are, it's basically sand here plus some toys, and you make some stuff with it. So when we're in the matrix sandbox, we're pulling out the new toys, and we basically have two things we have to learn about. First, we have to learn about the sand, which is the matrices. So when you look at the sand in this box, it's going to be this new mathematical object called a matrix. And then we also need to think about all the new operations or toys we're going to play with the sand, or with these matrices. And some of them are going to sound familiar, as you might expect, like we did with vectors and complex numbers. We're going to add them, subtract, multiply, etc. And so we're going to learn the first couple of these guys here today. And so that's where we're starting off, is with the sandbox. So here what you have now is you're going to have notes that you can follow along with if you'd like, and take some notes. First, I'd like to make a correction here. This is actually should say section 5.1. We are in unit 5. So this is just a holdover from last year. I'll get that corrected. And let's review and we're in chapter 14 now with our book. And so what we're talking about in this first unit here is going to be in chapter 1. And let's look at our learning target here. First of all, we want to define our matrix, which is sand, right? We got to take a look at the sand and see what it looks like. And then we're going to look at these first three toys in the sandbox, which are addition, subtraction, and scalar multiplication. So that's keep that in mind. That's what our goal is after going through this video, is to understand what these matrices are, what the sand looks like, and then these couple simple first operations that we're going to do. Okay, so first slide here is let's make a matrix, and here I just have a table of some information. So let's take a look at what's in here. I have this assume the distribution of boys and girls by class for a school like CJHS. I guess I need to change that to RZJHS. Is given by the following table. So we look freshmen here, we see we have 18 boys, 15 girls. This is just hypothetical at this point. Senior class here has 17 of each. This has a large junior class, 23 and 31. So a matrix then is a way to do this is, I'm just going to go ahead and write this in this thing called a matrix, and it's just going to put some brackets here, and it's going to extract the numbers out of this thing and just write them in there. 23, 17. You can see I'm preserving the order and the arrangement here. 31, 17. I'm going to close that off. Maybe we'll give it a name here like A, and boom, we've made a matrix. So I think from this you could probably get a sense so this is a piece of sand in the matrix sandbox that we've just created here. If we went in there, we'd take a look at it, we'd see we could find that one if we looked hard enough. So let's move on to the next page here. So what is a matrix? Well, as you can see by where I just created one, it's going to be this rectangular array of numbers. A key point here is it does need to be rectangular, and an array is just a spread of numbers with rows and columns. So any arrangement of numbers that's in a rectangular type form with some order to it is going to be called a matrix. And Typically you put brackets around it to indicate that it's this single mathematical object, instead of just, if I didn't have those brackets, you wouldn't be sure exactly what I'm doing with it. So here we have the brackets, and it says here some authors will use parentheses, so it wouldn't be unusual in some places to maybe see a matrix indicated like this, with rows and columns separated by brackets. Just like vectors, there was all kinds of notation we had to deal with. Most textbooks are going to use a bold letter A. Remember, in vectors we used bold letters, but it was lowercase, so the difference here between vectors is it's a capital letter versus like a bold V that we might have used with vectors. Sometimes you'll see an italic capital letter too, so that can happen. And then sometimes when you're just handwriting, since you can't really, your handwriting can't distinguish between bold and italics, just like with vectors. Sometimes with vectors we had to put a little harpoon above it, or sometimes like an arrow. With matrix, if you want to be clear that you're talking about a matrix, you can just put some brackets around it and indicate it that way. So this is just ways to label these pieces of sand that we've talked about. So a matrix here is a rectangular array of numbers. Rectangular is important. Just maybe before I move on, I'll talk about, like, we could think about something like a triangular array of numbers. Like I could put some numbers like 1, 2, 3, 4, 5, 6, some like numbers arranged in a triangle, and and maybe give it some cool looking brackets here. And maybe in your own algebra system you could invent sand that looks like this, but in our world here with matrices, we're going to say that that doesn't work because it's not rectangular. So again, that's an important piece of our matrix sandbox, is that it has to be rectangular. Well, who uses matrices? So someone invented this algebra system of matrices, and it actually has tons and tons of applications. Lots of interesting project ideas can come out of matrices if you're still thinking about what kind of project you want to do for our final. So some just real quick examples are, anytime you have information that's convenient to express in a tabular form, or basically a table, matrices can be really helpful. Like if I'm thinking back to the business world here, it wouldn't be unusual to have like a matrix where, let's say I want to just have my sales for for the year. Maybe in here I'd have January, February, March, April, etc. And maybe like product 1, product 2, and product 3, and then I'd have numbers in here. If I sold like 10 million in January for product 1, 5 million for product 2, and then 2 million for product 3, I could arrange that in a matrix like this. And so I could have this for the whole year, and then if I wanted to do some stuff with it, I'd have it all in one single mathematical object. If I wanted to increase everything by like 5%, I'd have it nicely arranged in this thing called a matrix. If we were in class, I'd ask you for some other ideas on examples, but here I just went and took a look at 2 other ideas of where matrices occur, just to give you a taste for where this kind of thing can happen. Here is a computer graphics application. So up on the top here, I'm just showing this cube, and this cube has some coordinates here, and we're labeling them like 1, 2, 3, and 4. And if you remember, for 3D coordinates, every cube is going to have, every point in 3D is going to have 3 points indicating where it is. So like in the X, Y, Z space here, this one might be, I don't know what it is going to be, it doesn't matter, 3, 2, 1 or something. And what we could do is represent the position of this cube in space by like a matrix here, which is essentially this would be like the X coordinate, the Y coordinate, and the Z coordinate. And then we could at any given time say where are points 1, 2, 3, 4, 5, 6, 7, and 8. And if we looked at that matrix, we'd be able to tell exactly where the cube is. So like in a graphics, like in a video game, that would be important, because this cube could be spinning around on the screen and you'd want to know where it is at any point in time. So the matrix can capture that information, and you would just store, like here, point 1 would be stored in that part of the matrix. Point 7 would be stored down here. I should have made that a little bit bigger. So that's one real-life example. And the second real-life example here is a page from a trading screen. So this is from a screen with someone who trades currencies. like euros for dollars or British pounds and that kind of thing. And what you see here is essentially, it's called a correlation matrix, indicating how likely different currencies are to move together. And this was as of some point in time, and don't really need to interpret the information here, but like basically a correlation is a number between, well, I'll go ahead and do it, between -1 and 1. 1 is perfect correlation. That's why down this diagonal here you see ones, because like for example here, the British pound is perfectly correlated with the British pound. But if I looked at this entry right here, this says there's a 0.71 correlation of the British pound and the euro. Looks like that's a euro dollar there. So, you know, you get the idea. And it just that people use this stuff in all kinds of applications. And you don't need to understand these different matrix applications, but I'm just trying to give you a sense that this is this stuff gets used in places. Okay, so move on. Let's go back to the math a little bit here. So we got some basic terminology just to understand. Again, when we look at the sand, I think you know what they look like now. There are these rectangular arrays of numbers, but we got to make sure we can take a look at the name, or just understand what all the different namings are. So the dimensions of a matrix, if I have, I'll just do like a quick little idea here, 3, 4, 5. The dimensions are the rows in the column. Since it's a rectangle, you're going to need to know that. And we almost always are going to write it as row by column. So we're going to call this matrix here there's 2 rows, and then there's 3 columns. So we're going to call this a 2 by 3 matrix. So when you describe the dimensions, now you have an exact picture of what it's going to look like. Not surprisingly, an element of a matrix is going to be a single item in the matrix. So like right here, we'll take that number right forward. That thing is going to be called an element. This matrix that I just drew here has how many elements? 6. There's 6 total elements. And then we're going to use lowercase notation for it to indicate that it's a piece of a matrix, whereas the capital letters for the entire matrix. And then we can give it an index value because we need to understand how to find it. So I and J are going to be the row and column numbers. So this element here would be called A. We're in the second row, so we're going to do it 2, and we're in the second column 2. So when I say element A2, 2, it's clear that we're talking about that exact element. As an example here, if we wanted that one, we're in the first row, third column, so we'd call that one A1, 3. Okay, and then we have the third item here, transpose of a matrix. Actually, I'm going to save that to the next slide here. And then we have row vectors and column vectors. Nice that terminology makes a reappearance for us. That is going to simply mean a single row or column from a matrix. So over here, if I wanted to extract this column right here, we could call that thing a column vector, and we might even write it like this, 1, 3, kind of like a little mini matrix itself. And that would be a column 1 vector. And you can see the parallel to being kind of a vector here. These are like the components of a vector. And this, why we call them vectors, will become even more clear when we talk about some of the tools. And then, if we wanted to, we could take a look at this guy right here. 3, 4, 5. We'll write it like that as a little mini matrix, and that's going to be a row 2 vector. Okay, here I have a quick example. I really feel like I went through most of the terms with the example I created on the last page. So all I'm going to really do here is do that transpose, which I skipped before. So if I label this matrix A, that's all uppercase, intended to be bold. If I call something AT, which is the transpose, that's what I mean by transpose. And transpose simply means that I switch the rows in the columns. So here we have row 1 becomes column 1. So when we make a new matrix with the transpose, row 1 becomes column 1, 1, 4, 6, 10. Row 2 becomes column 2. 2, 7, 5, 3. And there's some operations later where finding the transpose will be useful. You can also see that what we call, so we could have done it the other way too, that column 1 becomes row 1. So 1, 2 became 1, 2. Column 2 became row 2. Column 3 became row 3, etc. So you don't have to do it the way I did it here. You just got to flip the rows and the columns and make sure you keep them in the right order. So that was just an example of what transpose. So that's, I guess, our first official tool that we've learned. If you take a piece of sand from the sandbox and you want to do its transpose, you do this and you get another matrix. Note that this matrix was a 2 by 4 matrix. The transpose, because you switch the rows and the columns, becomes a 4 by 2 matrix. Okay, so here's just a list of the basic matrix operations we'll learn. So that we've moved on from sand to toys. And, you know, this thing right here might be our shovel. This is going to be a terrible looking shovel, but I'm going to go ahead and draw it anyway. This might be our, pail, and etc. So we have addition, subtraction, multiplication, scalar multiplication, and then we have these inverse operations. So where we're going to focus on today for this lesson is just these top 3: matrix addition, matrix subtraction, and scalar multiplication. Those are the first 3 toys that we're going to cover just today. So and then we'll cover the next ones in future lessons. All right, so matrix addition and subtraction are really quite straightforward. Matrix addition, so we do use a plus sign to indicate addition, just like we do in the real number sandbox, but let's make sure we know that it's a different toy because we're in a different sandbox, even though it looks similar to toys we've used before. And let's see what this says here. Creates a new matrix whose elements are the sums of corresponding elements. So if I just had a really simple matrix here, 1, 2, 3, 4, and I want to add 5, 6, 7, 8 to it, what this is saying is I find the corresponding elements. This is going to be very intuitive. In a lot of ways it's really similar to vector addition because you're adding components. This is a corresponding element. That's the first row, first column. And then I'm going to add that 1 plus 5 goes in that spot, etc. I'm not going to go ahead and do them all, but so you could see that the first element of our sum is going to be 6, and we'll maybe do the last one here. 4 plus 8 is 12. I'll go ahead and finish it. 3 plus 7, 10. And then the upper right corner, 2 plus 6 is 8. So this guy right here, if this is A, this is B, we've just created a new matrix, A plus B, by adding the corresponding elements. Subtraction, same thing, right? If subtraction, we can think of that as just adding the opposite anyway. So there you're just going to subtract the elements and get a new matrix. An interesting question to ask here is this one I have down here. How is this similar to adding or subtracting 2 vectors? Well, it's really similar in a lot of ways. Like if I had these vectors here, 1, 1, and 2, 1, how did I add those vectors? Well, I added the components, 3 and 2. Alternatively, I could have just thought of these things as matrices without no comma there. This is a 1 by 2 matrix plus a 1 by 2 matrix, and I add the corresponding elements, so it's 3, 2. So you can see that there's some real parallels here. In fact, a lot of people think of vectors as just matrices themselves, and that's going back to the definitions when we called them row and column vectors. You can kind of see why. So it's almost identical in concept. You're just adding the corresponding pieces to get the sums and differences. Alright, so here's some quick examples. Since these are easy, I went ahead and did them without while I paused the recording. And so you can do these on your own and just check your answers, but you can see here A plus B, what I've done is just added the corresponding elements. Like here, for example, the upper left corner is 2 plus 6, and then you get 8, 8, negative 1, 6. So that's the answer to A plus B, 6 and then 8 in the bottom corner. And here I'm taking A and subtracting all the corresponding elements, A minus B is going to be this matrix here. Now an interesting one is I asked what is A transpose plus B, so this requires two operations here. First is to be able to transpose A, and again what you do for a transpose is just make column 1, row 1 become column 1, row 2 become column 2, that's right here. And notice here we have a 3 by 2 matrix and a 2 by 3 matrix. So what's interesting is if you go ahead and try and add this thing, you're going to get stuck at some point because there's not a one-to-one correspondence between all the elements. So there's some questions about what would you do there. Would you at least try and add the ones that are in common? Looks like they do. They both have an A11 entry, so like a 2 and a 6. You could try and do something like that. But then when you got down to like this row here, this one has a row 3, this one doesn't. So the way the algebra creators have decided is if there's a dimension mismatch for addition, you just simply say it doesn't exist, right? You just can't add them together. They're like incompatible pieces of sand, and we just say the operation is undefined. So that's a key point for addition and subtraction, that they must have the same dimensions. And that's not going to be true for some of the other operations, and but anyway, we can go on from there, or go on to the next slide. So this is addition and subtraction have to have the same dimensions in order for it to be defined. Okay, next and last tool for learning today is scalar multiplication. This is going to look exactly like vector addition, or vector scalar multiplication. So we take a matrix A and we multiply it by a scalar. Remember what that is? That's like a single number without any, at least in the matrix space we said it didn't have any direction. Here it's just a single number has no dimensions to it. It's just and we get a new matrix. We're going to call it CA, just like we made a vector. Sometimes we called it KV, where each element is simply multiplied by the scalar C. So we just go ahead and, if I have A here, I want to find 2A, I simply double all the entries. So 2A would be 2 times 2 is 4, 6, negative 2, 4, 6, and 10. And if you recall, like when we did scalar multiplication of a vector, if I had 2 times this vector here, I'd have a new vector, which is just all the components scalar multiplied. And so maybe just see where you might use this. Let's do a real-world interpretation of scalar multiplying the opening matrix. So if I go back to our very first slide here, and I said, what does it mean if I compute 3A here? I'm not going to go ahead and do the numbers, but what we're doing is we're taking each element and multiplying it by 3. So the real-world interpretation of this is what RZJHS would be if we tripled in size. So if we could triple our enrollment and look exactly like we do in this picture anywhere, or in this matrix, that's what 3A would represent. It's a matrix giving the information of what CJ would look like, or RZJHS, sorry, would look like if tripled. And then the last slides here are just some properties of matrix addition and subtraction, that basically commutative property, distributive properties work as you might expect them to work, like they did for vectors. And again, this won't necessarily be true for the other operations we're going to do. And just maybe to kind of show you a little proof for this one here, if you wanted to prove, if I asked you to prove that this thing was commutative, what you could do is say, well, let's just make a matrix that's got X, Y, Z, and W, and call that A, and this is maybe A, B, C, and D. So the question is, can I reverse these things? Well, the way you would do that is you'd first write the sum, so X plus A in the upper left corner, Y plus B, Z plus C, W plus D. Now the plus signs inside the matrix here are the real number addition that we're familiar with. So because that's commutative, we could go ahead and reverse the order here. A plus X, C plus Z, B plus Y, D plus W. And now we can kind of reverse the operation here and say that this is A, B, C, D plus X, Y, Z, W, which equals B plus A. So we've gone ahead and improved it. And if you're interested, you can go ahead and prove these other two. I'm not going to do it here in this video. So now you should have everything. Let's just go back to our learning targets here and make sure that we've covered everything. We've defined a matrix. We've performed matrix addition, subtraction, and scalar multiplication. So you should be good to go on the problem sets for this first part of the chapter.